In the context of large language models, RAG stands for Retrieval-Augmented Generation. RAG combines the power of retrieval systems like search engines with the generative capabilities of neural networks to enhance the performance of language models. Consider the situation when you have several thousand documents of your organization. The documents can be holding information or documentation of policies, maintenance strategies, solutions to specific problems, diagnosis processes, or practically any text relevant to your problem space. You want the LLM to answer questions based on the several thousand documents you provided, not based on what the general purpose LLM was pre-trained on. There are two ways you can target this problem. One is RAG, that is Retrieval-Augmented Generation, which is today's topic. The other one is fine-tuning. We are not covering fine-tuning today. I have some other videos on fine-tuning, which I will link from the description section below. Okay, let us discuss Retrieval-Augmented Generation, or RAG. As the name suggests, RAG has three aspects: retrieval, augmentation, and generation. Let us start with retrieval. When the RAG system receives a query, a question, or a user prompt, it first retrieves a set of relevant documents or information snippets from a large dataset or knowledge base that you provided. This retrieval step is similar to looking up information in a library or on the internet to find relevant facts or raw data. The outcome of the retrieval step is generally chunks of text relevant to the user query. Now, the augmentation step. The retrieved information or chunks of text are used to augment the input to an LLM. This means that the LLM does not rely solely on its pre-trained knowledge. In addition to the pre-trained knowledge, along with the user query, the LLM has some relevant text from your data that the retrieval step returned. The generation step is obvious by this time. Practically, with the augmented input, that is the user query and the chunks of relevant text, the LLM generates a response. Because the LLM has access to more specific information relevant to your data, the response can be more informed, precise, and contextually relevant than the model's knowledge alone. The process is something like asking ChatGPT, "Hey, here is my question. To answer this question, please use this text that I am providing and do not extensively use your background knowledge on this. Rather, use the text I am providing." Of course, how you will design the prompt is up to you and somewhat depends on your downstream application. Now, let's take a step back to understand how the retrieval mechanism functions. The system for retrieval can be straightforward. For instance, you might segment the entire text into chunks, let's say chunks of 500 to 600 words each. Then you could compute the Jacquard similarity between the query and each chunk to identify the most relevant pieces. Alternatively, more sophisticated vector-based systems can be employed. A general-purpose LLM like BERT could be used to generate embeddings for each chunk. This involves creating an embedding vector for each segment and storing these in a database. To store the chunks and vectors, you can use JSON, XML, or an open-source vector database like Pinecone, Chroma, or Weaviate. When a user inputs a query, an embedding vector is generated for this query using the same model that was used for the text chunks. With the query vector available, the most similar vectors in your database can be identified. These vectors are linked to the text chunks relevant to the query, which the retrieval step then returns. You might wonder why the text needs to be chunked. LLMs, especially smaller ones, generally have token limits. To accommodate these limits, your text must be segmented, hence the need for these chunks. The augmentation step can also be enhanced based on domain needs. Various strategies can be used. For example, one can pre-process and filter the returned chunks based on domain-specific criteria. For example, in medicine, law, or engineering, the augmentation process can include steps to ensure that the language, terminology, and content format are aligned with professional standards and expectations. That is, the augmentation step can be highly customized to meet your needs. The vector database the retriever of the retrieval step uses and the augmentation can all be local at your end in your organization. The LLM can run locally on your computer or in a commercial platform like OpenAI. If the data you have is sensitive, you might not want to send the chunks to a commercial platform. In that case, the LLM has to be local, like Llama, GPT-2, or Mistral. Cloud-based commercial platforms might be a good choice if the data you have is not sensitive. Now the question comes, when isn't RAG appropriate? For queries like summarize the paper titled XYZ or what methodologies are used in the entire paper, RAG might fail because it will probably retrieve only a few chunks and answer the question based on those chunks only. Unless you customize your retriever step to handle such aggregation type queries or summarization type queries, RAG will not shine in answering questions that require many chunks or going over the entire corpus. In a past video, I wrote a Python program to have a conversation with local documents using OpenAI. I actually implemented a RAG system there that had the generation step leveraging OpenAI's LLM. In another video, I showed how to use chat with RTX, which is an NVIDIA software to query against local documents. That chat with RTX software uses a RAG system. The LLM is Mistral LLM, installed locally on the same computer where Chat with RTX is installed. I will provide links to both the videos in the description section.